Today we are very excited that we're going to switch to our topic a little bit. Last week, a couple weeks ago, we had John Zogby who talked about the science of polling and was more about, had a little bit of analytics applications in the social science, in the polling business. And before that, we had talks regarding nanotechnology. We also had some really high-tech mathematics talks here before. And today, we're switching gear a little bit, and we're going to be having the lecture on robotics. And robotics, certainly here at SUNYIT, we've had some really great beginnings with the future Lego League, FLL, and also, and we're growing in that area with more and more advanced robotics program for our community, high school, and now hopefully at SUNYIT in our undergraduate and graduate programs. But anyway, today we're very excited that Professor Michael Gennert from Worcester Polytechnic Institute is here with us. Now, Mike is no stranger to SUNYIT. I think some of you might remember him from a few years back when he was with PAR Technologies and also taught our Pascal course here, correct? And now I'm dating myself a little bit back in that, yes, I used to program in Pascal, and in fact, I still program in Fortran 77. So nobody says it's a dead language. Okay, it's not Latin. It's not it's not that kind of language, but it's still very useful. But since leaving SUNYIT and PAR in the Utica, greater Utica area, Professor Gennert has been with Worcester Polytechnic most of his academic career. He received his bachelor's and master's in electrical engineering from MIT back in 1980, and has received also, he's sort of a trifecta MIT, his doctorate also in electrical engineering from MIT in 1987. And he has been with Worcester Polytechnic, or we just say WPI, growing its robotics program since its inception, and we are really excited to have him back here at SUNYIT. So without further ado, I think I'd like to introduce Professor Michael Gennert of WPI.
All right, well, thank you, President Ye, and thank you, Bill Durgan, for inviting me, Provost Durgan, and thanks for coming here. So, I'm going to talk about robotics engineering, and I'll talk about what we put together here for education and research, and also have a little bit to say about academic leadership and how to make things happen. All right, so some things you might be interested in hearing about. So I think President Ye must have read my slides. I went to MIT for 5 years, got my dual major in computer science and EE, a master's degree. And the thing was you could get all three with one thesis, which is what I wanted to do, just write one. And I co-opted at GE in Pittsfield. And then went to PAR Technology Corporation. They were in Rome at the time, then moved to New Hartford, and I lived right here in Utica, and the apartment I was in still exists. Okay, and while I was there, I taught Pascal as an adjunct in the old factory. Fond memories, and I had a great time here. I don't know if you realize just how good life can be in this area, right? But I used to swim, sail, ski, hike, run, play Frisbee with friends, go to concerts, go to Munson Williams Proctor, and met my wife here, and so you've got a lot of things going for you as a place to live, in case you forgot. Back to MIT, Got my doctorate in '87 in the AI lab, and then went to WPI, all right, where I've been ever since. And I rose to become computer science department head, and now I direct the robotics engineering program, and that is a tale. So, robotics. Here is the cover from Popular Electronics, 1956. Okay, so at that point, you know, people were thinking of robots as science fiction, right? Haha. Best wishes for an exciting robotics Christmas. All right, well, so what's a robot? Let's start there. So as we define it, it's something that senses, has to perceive the world, then has to compute and decide what to do about that, and then act, and then that affects the world, so we have this cycle, all right, where you've got devices that interact with the world and change the world. So here are some of today's robots. Actually, this is an old slide. This slide is 5 years old. So this is actually yesterday's robots. Let's go look at today's robots. They're actually quite a bit different in some ways. All right, so there, in the upper left, you see an underwater hovering robot for doing ship hull inspection. Right? That robot actually is the first naval robot that the DoD is building as a program of record. Right? Now, if you're not in the military, that might not mean much to you, but for the military, a program of record is when they really start building a lot of these things under long-term contracts. Thank you. So, you know, aircraft carriers and bombers, and, you know, those are programs of record. So that's important. And then there's, on the top, there's the Global Hawk, which is, you know, a robot. It goes autonomously. There's the Mars Curiosity rover on Mars. And then we have Kiva Systems robots, and they do order fulfillment in warehouses, those little orange robots. That company was just bought by Amazon a year ago for $775 million. Okay? These are not toys anymore. This is a real industry. Then you have the Da Vinci surgical robot, used in surgery, mostly for minimally invasive operations. So this is really being used today. Then we have the LS-3 that DARPA has ordered from Boston Dynamics. This is basically meant to be a robotic mule carrier supplies around. A couple of telepresence robots. In the middle is Baxter. Baxter is a new manufacturing robot from Rethink Robotics. That robot, Baxter, is meant for manufacturing. It costs $27,000. Okay. It doesn't cost $100,000, and it sets up in an hour, and you can train it in 10 minutes. And we're ordering one for our labs. I'll tell you how it works. Ask me in a month. All right. So this is going to change manufacturing. This device will let people, hey, if you can assemble stuff for the same cost or less here than in China, guess what? We can do that here. Wouldn't that be nice? All right. Next to that is the Luge. This is a robot from iRobot that cleans gutters. Small market, but kind of cute. And then we have a video from GE, which I think is worth seeing. So GE's recent ads have focused on robotics and other kinds of automation. And, you know, GE doesn't play games, right? This is a serious company. And so if they think that robotics,
the machines are on the move,
is important,
they're curious.
maybe
Because they've
you're onto
heard
something.
that there are new machines, brilliant ones, and they're coming to see for themselves. Machines with the technology, the scale, and the ability to communicate, to make the world work better. And And now all the machines want in.
Yeah, how cool is that? All right, so these advances in robotics, what makes them possible today are these driving factors. Now, I'm sure you all know about Moore's law, right, which says the power of computing devices doubles every year and a half to 2 years. But there are other laws as well. Crowder's law for storage capacity, Butter's law for networks. And so everything you need in a robot gets better, faster, cheaper. So here's Moore's law, right? We all know that. Doubles every 1.5 to 2 years. Here is Moore's graph from his original paper, extrapolating from 1959, 1 transistor, up to 1965. Well, that law has held up till now. 54 years later, from when he started, that means about 27 to 36 doublings. So, those of you who are computer scientists know how to do powers of 2, right? We should have devices that are 128 million to 64 billion times as many devices. Where are we? Right there, right? Chips now can have up to 7 billion transistors. And that law seems to keep on going. All right. Crowder's law for storage capacity. Same story. You can go to newegg.com and buy 2 terabytes of storage for 80 bucks. All right. Who here used punch cards? All right. Almost half the people. All right, good. All right. So, how many punch cards is that? It's a lot of punch cards. In fact, it's the JFK, 60,000 tons. That's a lot of punch cards. Right? But since we're near the AFRL, it's also more than 600 airplanes, B-52s. Okay, that's a lot of airplanes. It's also a good fraction of the Library of Congress. So for 5 of those boxes, 400 bucks, you could store the entire Library of Congress. 400 bucks to store it all. And this law also applies to storing DNA data, right? All right. Butter's law, very fast networks. So the fastest network now, they've shown that you can get 100 terabits per second over optical fiber. Whoa, that's fast. Nice job, John. Photonics is cool. All right. And robotics has followed these exponentials. So whereas the Stanford AI cart in '79 went pathetically slowly, it took overnight to cross a room. And in a few years, we now have the DARPA Grand Challenge where cars drive themselves across the desert. And of course, they're going to drive themselves in the streets too. So here's the equation. Here's what's going on. All the parts of robots, the sensors, computing, actuation, communications, all drops in cost and goes up in price, except for the actuators. My mechanical engineering friends, you're letting us down. You got to give us cheaper actuators. But everything else keeps falling in price. And the needs keep going up. Right? So for defense, security, elder care, medicine, home care, consumer robotics, maintaining the homes, manufacturing, entertainment, nanotechnology, all those things have an increase in need. So those two lines will cross at some point. So they crossed years ago, 10 years ago, for vacuum cleaners. And so at the time, robots were doing the 3 Ds, tasks that were too dull, too dirty, or too dangerous for human beings. But they're now more capable, so they can do jobs that are too even clean for humans. Right? So, if you're going to build a nano fabrication facility, how do you make these chips? How do you make these devices? You can't have any dirty humans in there shedding cells and dirt, right? Use a robot. All right, so robotics in the country has sprung up around several main loci, right? We have robotics in the Bay Area, in Michigan, in Pittsburgh, and in greater Boston, around the great universities especially. And some other schools have also had robotics spring up near them. So you've got New York City and Atlanta, where else? Texas has a few spots, Los Angeles. So where I'm from, in Massachusetts, we've got a really strong and vibrant robotics industry. In fact, this slide's about a year old and it's way out of date. There are more companies here than are shown, but there are 100 companies or labs in our local area. All right. And they're doing over $1 billion in business. Well, with all that industry doing robotics, we should educate people for this industry. So what's needed to do robotics education? Now, as the picture shows, you kind of need three things. You need double E, electrical engineering, computer science, and mechanical engineering. Now, of course, you can't fit 3 degrees into 4 years. Okay? So what do we do? Well, we'll talk about that in a moment. So, undergraduate robotics was really of kind of two flavors. Associate's degrees, and those tended to focus on automation and maintenance and technician level work. Okay. And at the BS level, a lot of schools have a course or two in robotics. Some might have minors even, or a focus area. Georgia Tech calls them threads, something like that. But nobody had a major. At the graduate level, you've got a few schools that have robotics degrees. Carnegie Mellon was the first, and so we have a few others, and WPI. So we saw that there's this education gap, right? Where on the one hand, you've got technician level and robotic technology programs, and then you have the research level programs. Let's call that robot science, all right? And that work is many years or decades from being commercialized. So there's this gap, though, of engineering. And to fill that gap, we created this program, a BS degree in robotics engineering. So educating engineers to design and develop robotic devices. And also, we added to that the PhD. So now we kind of span from K-12, where we run some robotic outreach, and we have FIRST and so on, up through the PhD in research. So one of our slogans is making useful robots, right, the engineering side, and also making robots useful, the research side. And a few of the schools have announced or started majors in robotics. UC Santa Cruz, Lawrence Tech, UDM, Detroit Mercy, and I've talked to my friends there and helped them to get that rolling, and Carnegie Mellon. But that's only the second major for them. All right. So how hard can it be to start a program? All right. Well, it's a lot of work, right? But it's worth it. And here's why. We've already seen the robotics equation, right? The importance is going up on the supply side. You've got tech capability and decreasing cost. On the demand side, you've got the pull of the needs for robotics and applications. And at the K-12 level, there's great interest in robotics. All right, so you're holding your FLL competitions here, and you know how kids love to do that. All right, so we do that too. We have FIRST teams, and so let me play a little video of FIRST. This is 2007. Our robot there, Team 190, won the World Championship that year. That's a great design of a robot. So you've got kids who are really excited about working on robotics in high school. They work really hard at it. There's Ken Stafford. That woman there works at Honeybee Robotics now. She went to Genoa for her master's degree. All right. That guy works at Bose. You might wonder, why does Bose hire a robotics guy? What does Bose do? Bose builds speakers, right? So what's that? Well, it's a circuit that drives a coil that makes a diaphragm move. They also use that technology to build car suspensions and high-end car truck suspensions. So what does that involve? You're going to sense the vibration of the vehicle, compute what to do, drive an actuator, see what happens. It's robotics. Not a robot, but it's robotics. All right, well, that's enough of that. Okay, guys. Shh. Anyways, I could watch that all day long. That's great. So those are the kind of kids you want to have on campus, right? People who have that kind of enthusiasm, team spirit, who really understand how to build stuff and make things happen. All right. So that's weird. All right, there we go. All right, so where are those kids going to go to college? Well, build a program that they can follow on to rather than being told, I'm sorry, you can't use robots until you're in grad school. Right. And it fits us well because we have these strong programs in computer science, electrical engineering, and computer engineering, and mechanical. We've got a project-based curriculum, so we already are hands-on. We've got that Team 190, and we can also be leaders and have leadership. All right, so who are Schmid, Marmot, Riest, and von Gunten? Who are those people? No one knows, right? No one knows. All right. Who are Hillary and Norgay? Well, of course, Sir and Hillary climbed Mount Everest with Tenzing Norgay, right? First team up. That's the second team. Okay, you got it? Good. All right. So if we're going to do a program, let's talk about education as a business. Now, faculty, we never think of education as a business. Well, almost never. My sister teaches at Southern Connecticut. I asked her, what business are you in? She looks at me, what do you mean? What business are you in? Well, she teaches women's studies, so she doesn't really think about that a whole lot. All right. But we're in a business, right? Yeah, right. We're nonprofit, so it doesn't apply to us. Yeah, right. Okay. You got to have revenue that's greater than your expenses, of course, right? And if you want to have a program, you're asking your university, your provost, and your president to invest everything, money, energy, time, people, space, all those scarce commodities. And not for fun either, right? This is to generate something real, right? To get a return of more money, tuition, funding, prestige, growing a business, growing industry here, right? A new program is a business decision. You don't do it because you want to. All right. I know they get it. You guys get it. All right. All right, here's a Form 990 filed with the IRS where you list every university, every private university lists its expenses and revenues and all that. There's a balance sheet, and you want to make sure that you do okay. All right, how do you start a program? Oh, this is a fun story. You hold an academic planning retreat. This is what we did. And then throw the plans away. How did that happen? What do you mean? All right, so here's the agenda for our academic planning retreat in 2003, 10 years ago. All right, and the president, the provost, the associate provost, that's him, William W. Durgan, all right, planned for this retreat to start new programs. Oh, and there I am with one of my little ideas. So we had this idea to have these new programs, and we were looking at what would be the future education we could deliver. Well, it turns out, where are they now? Sorry, Bill, none of them worked. Actually, one did, I'll get to that. One of them worked out, and it wasn't mine either. But there was this wild card session for some other idea, all right? Anything else that we didn't think of. So we had comms and networks, media, MEMS, bioengineering, dynamics, bioinformatics, imaging. That wild card session led to us having a major in interactive media and game development. Okay. And then we had a degree in liberal arts and engineering. And then we had robotics, there we are. Then we had environmental engineering, systems. Finally, 7 years later, we produced one of those ideas came to fruition, bioinformatics. And we've also done architectural engineering, and we do security as well, cybersecurity. Okay. So the idea of starting new programs is what really mattered. And so the leadership of the school made a huge difference. They happened to pick the wrong ones, but they got us going. All right? So the administration, you guys really do matter, despite what the faculty may think. Leadership matters. All right. And so here's our interactive media. How'd that happen? I'll tell you how we did this one. I was head of computer science. The associate head, David Finkel, said to me, Mike, we should do computer games. Yeah, we can do it with humanities and arts. All right. So we coordinated a spontaneous show of support. Think about that for a second. All right, bad joke. But we did, and it took off. All right. So let me talk about leadership for a moment here. In 2003, I was appointed as computer science department head. And of course, I had no experience running a department, so what do you do? How do you run a department? Well, so my goals were, number one, to survive. Number two, don't screw it up. Those are probably the same goals, actually. And I did this idea, though, of taking care of young faculty, because being faculty is actually a hard job, and it gets harder. It gets more demanding, right? You can do everything here. You got to teach well, bring in money, advise students, right? Play with robots, do K-12 outreach, all that stuff. It gets harder. And we had an advisory board for the department, and they said, wrong. They said, Mike, you are the CEO of Computer Science, Inc. What the heck does that mean? Your job is to grow the business. Grow the business? I'm an academic. We don't do business here. I'll bet if you took all the faculty in my department, they probably have had a total of 0 courses in business. What do we know about business? If you don't know it, you got to learn it. So how do you be a leader? So I decided to read some stuff. So I read Patton. You know, Patton's a great general, right? And a great movie, too. So he knows how to lead. Figured take some tips from him. I just won't slap anybody around, although some days I'd like to. Can't do that, right? Can't give orders, though. You got to work with people. So there's Patton. And then there's Patton. Then there's Machiavelli, the prince. Now, I'm not saying that you should be Machiavellian, but if you're going to work in academia and administration, you have to understand that some people might be playing Machiavellian games. And then I also read The Art of War by Sun Tzu, great little book. All right. So when Jim Hendler became head at RPI, I told him this. He goes, Mike, you're scaring me. But I think it's reasonably good advice. So in The Art of War, Sun Tzu has these big lessons, big themes about how to lead, all right? How to observe trends, how to use spies, ooh, all kinds of good stuff there. Understanding the terrain. All right. And actually, much of this is really useful information for any leader even today. Although how you manage concubines, that's not so relevant anymore. All right. But one of the big points was know your terrain, know where you lie. And the advice he gave was when you're at a crossroads, when you're at the area of intersecting highways, make alliances. What's that got to do with us? Well, here are those majors we started, and here's computer science. It's at the crossroads. Everyone, almost, relies on computing. You have to understand this stuff. So interactive media and games involves computer science. Liberal arts and engineering, robotics, systems, bioinformatics, cybersecurity. All right, so we skip over architectural, although you know what, there's a role for computing in architecture too, and environmental. So that's what it is about leadership, okay? You make alliances when you're in an area like that. So we had a vision of becoming an exemplary center for research and education and innovation in robotics. So we started with the BS degree, and the goal there was to grow the engineering talent, the people, for the 21st century, and grow the industry, supply the talent, start companies. At the master's level, we wanted to focus more on products and how you would think about systems and have technical leadership. PhD is all about research. All right. So the key ideas in our program was, first off, it has to be multidisciplinary. It has to include computing, electrical, mechanical. And then we use a spiral curriculum where we teach topics in the intro course and then go over them again in more detail in a unified robotics sequence. Each of those courses, Unified Robotics 1 through 4, has some elements of computing, electrical, mechanical. But each one has a theme. First one's actuation, then sensing, then manipulation, then navigation. We also include social implications. Robotics is a disruptive technology. You have to know what's going to happen as best you can. What are the effects of your technology? And I'd rather have an engineer who understands that do the engineering than someone who doesn't. We also included entrepreneurship. It was project-based, and this is both newfangled, right? Robotics is new and cool. It's also old-fashioned, all right? It spans disciplines. There's no boundaries. Look, when Roebling built the Brooklyn Bridge, he didn't say, I don't understand how to do wires. He just found out how to do it anyway, all right? So there's nothing you can't do. So it's never not my job. These kids will do whatever it takes. We had some principles we outlined, so we have to have clear objectives, make it broad-based to incorporate the three fields of CS, electrical and mechanical, has to be flexible, fit in 4 years, fit our philosophy, and be accreditable. So objectives, basic understanding, apply that to design and construct robotic systems, and have imagination and the entrepreneurial spirit, have ethical behavior and standards. All right. So it's broad-based, flexible, just fly through this. Fits better in 4 years, fits our philosophy, it's accreditable. So accreditation means that we've got credibility, and on a polytechnic, you have to be accredited. And also it helps for the FE exam and for ROTC. The current head of ROTC kept asking me, are you going to get accredited? Are you accredited yet? Because their students have to go to accredited engineering programs. So yes, we are. And how did that turn out? We got a visit from ABET in the fall of 2010, and they said, I can quote this, what you've done compared to a stovepipe mentality is fantastic, but you have one problem, your students are way too enthusiastic. So they approved the major, and we got accredited. So what's the major look like? Well, we made a first pass at the curriculum. We said, all right, you have to know some embedded systems, you have to know software engineering, you have to know statics area. We have all that. Let's just take that and put it into a program, tie it together, wrap it around, and make that the major. How hard can that be? So we did it, and there it is. So it fits. Proof of concept. There's one problem, though. Where's the robotics in the robotics major? Oh, there it is. That one course. All right, so not real good. So we threw it away and started over. This time we thought a little more deeply about it. And we decided to rip out the middle of the curriculum and teach the same material more or less in robotics. Now, we don't want to teach everything from scratch, so let's let the experts in computer science, EE, and mechanical teach the first courses there, okay? They can do that. Then we have the unified robotics sequence, and we fold in other courses as needed, kind of just-in-time education. So we fold in DiffEqs, linear algebra, probability, controls, embedded systems, and so on. And of course, we have advanced courses, and then a capstone. And by the time the students get there, they are totally project ready. Okay, so that's how it looks now. And here's curriculum 2.0. Our new version. Where's the robotics? There it is. Starts freshman year, goes to junior year, sophomore, junior year, senior capstone, electives, and so on. Oh, by the way, we have these funny 7-week terms at WPI. How does that work? Well, take a semester, split it in 2, and kids take 3 courses at a time. That's it. All right? Kind of strange, but it works. Works pretty well, actually. A lot of reasons for that. So, that'll work. And that's just one. There are thousands of ways you can go through the curriculum. This is not lockstep. All right, so let's see what people do here. Here's one of the courses. So here's a video the students made from a sophomore level course. And this is
every time it sees a tick,
to build a farming robot. Okay.
The lights will flash.
So you get farms here, right?
It was a good debug tool, so we could
What do you
see.
got to do?
We could see every time it actually
Drive around the track,
counts a line.
follow the
We
line.
can tell you before it actually
By the way,
happens.
the tick marks tell you how far you've gotten, so it's a little bit cheating, right? That's okay. So you got to get the tail,
You can see
then you
our
have to pick up a
robot
wagon
actually rotates its
and
wheels.
drive that around.
Accomplish sideways movement.
This has a great mechanical basis here, right? Look how those wheels turn. Isn't that cool? Right? We didn't tell them to do that. There are many different designs. This is that one team's design. Oh, try to get the apple. It fell down. By the way, robotics is all about making things work in the real world.
No, we're just gonna go with it.
One of our faculty wanted to teach the course with simulation only. I go, no way.
As you can see,
Deal with noise, errors, dirt. Life's messy. Okay. Hit the button for the drawbridge, so it went across the bridge. Next job is you got to pull out the
We
weeds.
designed it this way.
carry the apple all the way over there, of course.
Okay. Pulls the weeds.
Oh, wait.
Then it has to go and water the plants. Now, water and electronics don't mix very well, right? So we don't have real water in the bucket. It's just paper.
We could have it back.
We're gonna get it back. Next one.
Here's the bucket. Good. Did that. And the last thing it has to do, it's a farming robot. Few farms here, right? So, tip the cows. Here are the cows. No real animals were harmed in this experiment. We did grab one.
Now I can see how some of those cows are temptated. Mustache cow.
Dump the cow. Take a bow, Mr. Robot.
All right, very good, very good.
Okay, not bad, huh? They had fun. All right. How are we on time? All right. We have other videos here. I'll show one more. I mean, every class has some videos. This one is a mapping and navigation robot. Okay. And notice this one's not following lines, it's on its own in this maze. So mapping and navigation is a topic you might see in graduate school in a grad course in robotics. Right? This is a junior course. So we've built up to it. Okay? And they've already had probability, linear algebra, so they're ready for this kind of work. We don't tell them this is graduate level stuff, so the juniors do just fine. Yeah. And there's the map of the world it's made. Not bad for third-year students, huh? All right. Okay, so you get the idea of that. Oh, by the way, they're very hardworking. So this is the course evaluation from my class that just ended last Friday, a week ago. Ooh, wow. We're on term break now, so that's how I can come here. So, top question. How many hours do you spend in class in lecture and lab? And it's supposed to be 6 hours, 4 hours of lecture, 2 hours of lab. So most kids spend 6 hours. If you spend more than that, because you're stuck in lab, and one person spent 4 hours, I think he skipped the labs. I suspect he didn't pass the course. And then how much time do you spend outside of class? Most common answer, more than 21 hours a week, so you add it together. And typical student spending, I don't know, 20 plus 6, so 26 hours of a week on that one course. Wow. You think they learned something in 26 hours a week? Kind of hope so. All right, so that works. We have Capstone Projects. So here's some projects. On the upper left, there's a penguin for autism, right? So if you make a robot to play with kids, the robot doesn't get tired of doing the same old thing to help a student be more engaging. On the right is a roof robot to inspect roofs. We were hired by the travelers to build this because this is a dull, dangerous, dirty job. When there's a damaged roof, send a person up to the roof, and they might fall off, might fall in, right, all kinds of problems. Send a robot. There is a robot for doing following an obstacle course, a robotic quadruped, a bomb disposal robot, and a couple of walking robots that our kids have all done as their capstones. And here's one that was an award-winning project. This one's worth seeing. This robot was designed to enter a competition by NASA to build a rover. This is actually the second version of the robot. The first version, the previous year, won its competition. And if you look at that robot, you think, wow, did NASA build that one? Well, no, they didn't. These are 4 really good students. This is the dream team. So they graduated. 2 of them went to Carnegie Mellon for their graduate work. They met Red Whitaker, and he just basically said, "You're working for me." Another one is working for a company near us. And the fourth one is, I'm not sure where he is, but he's working too. So, pretty cool robot. When this one competed in its competition, it got more points than the other 10 teams combined, which included Caltech, by the way. We're kind of proud of that. Full disclosure, it was Caltech freshmen that we beat. All right. So that's that one. Where are we here? Yeah, that was a heck of a project. And of course, we have a little bit lighter side, the robotic kayak here. I think we'll skip over that video. If we have time later on, I can come back and play it. And then here's one. Where this team built a robot to do navigation, and this team won the Rookie of the Year award for their competition. They had a lot of fun building their robot, and we're building another version this year. And so you see the robot pulling the kids around the campus. They have a lot of fun, you know, they make these nice videos, kind of tongue-in-cheek. Programming, this is robots, right? Programming in motion. If you don't program it, it's a statue. Now, my mechanical friends say, if you haven't got a mechanical device, then it's all virtual. You've got a game. Okay, I'll concede that. So anyway, now I'll just stop that one. They have fun. And we've been able to get companies to sponsor these projects. So Boston Engineering, General Dynamics, Lincoln Labs, and so on. They're happy to do it, get some great publicity, get some access to really smart kids. And so the program as a whole looks like this, more or less. We have some gen ed requirements on social sciences and our junior projects and phys ed and humanities, a bunch of math and science, which ABET requires, but we've done it anyway. WPI requires you have a capstone and some free electives, and then here's the robotic stuff with electives and core courses and so on. That's how it looks. So a bunch of everything in there. All right, I'll tell you the little dirty secrets. I'll level with you. Not everything fit, okay? We don't require courses you might have thought you'd need, like algorithms, like AI, like signals, like design. Okay. Well, those are available as electives. So we have 4 years of good stuff, though, all right? We have all these faculty members who are involved in the program. So everybody wants to get on board. And you can see the majors, mechanical, computer science, electrical, and computer engineering, also humanities and arts, and social sciences as well, surprisingly. And here are the students. We had this event to kick off the program. Had a lot of interest. Maybe just because we had pizza. That always works. But we had a business plan. That business plan assumed we were going to get 15 or 20 kids a year in the program. And day one, 85 kids showed up. Oh my God. Well, that's the problem that you want to have. All right, so they've been getting jobs and internships at places like, well, Archaic. Archaic builds mosaics using robots. So the old way to make a mosaic is you draw out what you want, and then you get these tiles and you put them in place one by one. Oh, that's so dull. Now, draw it out, scan it, robot puts the tiles in place. All right? Makes perfect sense. BAE, Bluefin Robotics. and on it goes. iRobot's in there, Energid, Lincoln Lab, MITRE, Segway, Kinetic, Symbotic. All right. We've got more than 100 grads already from the program, and depending on how you count them, and that's always a question, how do you count them? We've got between a 90 and a 94% placement rate in grad school and jobs. Not bad. Here's the New York Times front page of the Education Life section, bemoaning higher education, but pointing at WPI as a counterexample. And there you see, right there on the cover, one of our students and a robot. Okay. Well, it's not quite the Rolling Stone, but we'll take the cover of the New York Times. All right. Lessons learned. What did we learn from all this? You need vision, you need passion, and a business plan. Okay? All three. That bottom up worked better than top down. And top down works better than bottom up. Huh? Well, it all depends. For faculty buy-in, this was bottom up. This was a faculty initiative that we were passionate about making happen. We got folks together and we did it. But for designing the curriculum, for planning out the major, top down. Stick to your principles. Know what you really want. But on other things, be willing to compromise. And I got really ticked off when faculty governance looked at our proposal and came back and didn't approve it. This was CAO and CAP, Bill. So what do you do about it? Maybe they're right. We'll accommodate them as long as we stick to what we really believe in doing. Communicate and cooperate and be bold. All right, those are the lessons. That's how you do it. How do you win? You have to have three things come together: academic merit, business merit, and politics. And we had all three department heads on board, me for computer science, the head of electrical, and the head of mechanical, so we could do it. And as SRI CEO Kurt Carlson says, no champion, no project, no exceptions. We've also got global projects, that's worth mentioning. Been involved in competitions. All right, we've mentored first teams. And in fact, right now, this is Friday, if they can, they should be competing right now for the first regional. We have 48 teams signed up to compete this weekend. You know, we could probably just fire the admissions office and just admit those 48 teams. And that'd be one heck of a freshman class. You know, those kids have passion. All right, we've been involved with NASA, other competitions. Yeah, oh yeah, how about that? 2009, Paul and his co-workers won the $500,000 NASA competition. Well, there goes Paul's financial aid. Actually, and he was cut a check for $500,000 by NASA, which he shared with his collaborators. But it went to Paul. We won last year's, and also this year's, NASA Challenge. All right. That's the undergraduate program. How are we doing on time? All right. We've got about half an hour left. I'm going to kind of fly through the master's and PhD. We did that, did that, did that, did that. That's on the test. Okay. Got it? Entrepreneurship. This is important. We really want to see enterprising engineers, not cubicle, I want to say cubicle rats. I won't say that. All right. People are going to get out, understand the business. So for the BS degree, we require a course in entrepreneurship. And for the master's, we require some course in business and one in systems, so they know what they're doing in a broader context, not that they're going to be inwardly focused. And for the PhD, they have to do something on professional leadership development, whatever that is. But it's not a course. It could be advising projects, could be a lab internship, something like that. All right. So let's talk about research here, because this is cool stuff too. We have several areas of research. You see, on the top right, we have human-robot interaction. Below that, it's a PR2. We actually have two of them on campus, but one's a loner. We have sensitive robot to grasp things. We have surgical robots, and we have work on locomotion and controls. We've got funding from NSF, NIH, NASA, DARPA, DOJ, industry, also the Air Force. Let's see if this one works. So here's a little summary.
WPI offers faculty and our
Oh, what does
students
he know?
a chance to really get to the leading edge of robotics research. Our research spans many of the important areas of robotics, including human-robot interaction, medical robots. Any place a robot can go, we're working on that.
And WPI is a great place for robotics research because of the diversity of fields that are represented here. the
Great
diversity of
faculty here
students.
too,
Part of our
except for
research is very
myself. but
strongly rooted
He's from
in
MIT,
understanding
she
what
was
we
from
need,
Carnegie Mellon.
and then taking that as
He's a
the
fellow of
starting
AAAI.
point to build robots.
That's the
that,
Association for the
will interact
Advancement of
with people in
Artificial
similar
Intelligence.
ways. And so there's an empirical sort of psychology, linguistic component, and then there's a hardcore engineering component. You actually have to make the little pieces work. There's the software, the hardware, the electronics, the mechanics, and all of that.
The research we're doing is to understand
She's also
how
MIT
it is
person,
that people communicate
Cognitive science and
both
AI.
verbally and non-verbally.
A fellow
We
of
use our hands,
AAAI.
we use our eyes, we look at one another, we point at things. We are excited about getting a robot to be able to do all of these things. It's very cutting edge kind of work, and it's challenging because it's at the interdisciplinary point between robotics, computer science, linguistics, and psychology.
Are you curious about what I can do with all that?
My research is inspired by the problem of enabling everyday people to use robots. More importantly, not just control them, but to instill in them new capabilities.
My research is called sensitive robotics. Sensitive robotics is about making the robot feeling the contact with the world using mainly tactile feedback, the same way that humans and animals do. Using that information, we can make the robots smarter the moment that they try to execute a task.
My research in the WPI Automation and Interventional Medicine Lab is really focused on medical devices and surgical robotics. I'm really excited about the work that we're doing now in the WPI AIM Lab because there's really this opportunity to make a huge contribution into the medical field. The idea of integrating robots into surgery is relatively in its infancy. There are very few commercial systems out there at this point. And then taking this to the next level of integrating real-time imaging, and in particular, really high-quality real-time MRI imaging, just opens up the door to so many new medical procedures.
It's been very exciting to be part of robotics research for the last decade. It's such a rapidly growing field that's evolving at a pace not matched by many other areas. And we're
And it
really
looks kinda
starting to
clunky.
see the ability
If
to
robots can
get
do
robots
this
out to where they can be
now,
helping
right, what are they going to do in
In
10
a very
years,
short time,
or
we've
20
come
years,
from
or 30
having the
years?
seed of an idea in robotics to being recognized as a world leader in robotics, engineering, education, and research. So I don't really know what we'll have for robotics in the future, but I know that we can educate the people to make that happen. And that's pretty exciting. So there's the HRI area. Medical robots. Yeah. Sensing. Navigation and autonomy. Kinematics. So now I've got a bunch of slides on some of the projects in more detail. So I'm working on a project on Bayesian visual odometry, which means using cameras so you know where you are better than you could without cameras. So NASA wants to send robots to the moon, to Mars. No GPS. What do you do? Or if you want to have robots drive around through buildings, no GPS. All right. Or if GPS is denied, how do you know where you're going? So that's the problem we're working on, is using IMUs and characterizing how they work, find the noise, and then using that to update where you're working. This is supported by NASA under a SBIR with a local company. All right, there's our little robot. Kind of cool stuff. All right, we have this lab for autonomous robotic collaboration, and that robot's name is Archie. You know, robots can get you some really
WPI unveiling
great
a
publicity too.
state-of-the-art robot Monday meant for research at the school. Assistant Professor Dimitri Berenson received an award from robot manufacturer Willow Garage
There's the
Incorporated
PR2.
for his contribution to open source software. The plan for the robot, who's named Archie, is to be a research platform for investigating human-robot collaboration, motion planning, and robotic manipulation. Possible uses would be for robot helpers for the elderly or disabled, and also in manufacturing, where they can work alongside humans.
Robots that are going to be able to perform tasks in those kinds of scenarios, and we don't have
We just hired
those
him
yet.
for this
So
fall.
we need to conduct this research to figure out how
Cornell
to make
undergrad,
robots
Carnegie Mellon
useful in those
PhD,
scenarios.
Berkeley postdoc.
Archie arrived at WPI over
Kind of
the
faculty
weekend
you can hire
and
for
was introduced to
robotics because they're
students
not
and
all going to go to
faculty
Carnegie Mellon
just
and
this
MIT.
evening.
So you can really get some top-notch talent. All right, that's his lab. Soft robotics, just hired Chadish Onov. And let's see if we can get this thing going. Hello. It's not moving. Rats. Huh. Software problem. All right, anyway, soft robots. Sensing the world. So here you have robots that have sense of touch. That's a great area to work on because robots right now, you know, don't understand what they're holding on to very well, right? Typically they have, you know, one sensor on their claws. If you want robots to work with you, they have to know when they're patting you on the back, when you're pushing them, right? Because humans have this great sense of touch all over our bodies. Robots are totally sensory deprived. If you could make low-cost sensors, you can make them grab things better, and also for walking, because when you're walking, you want to know what are you walking on. Is it hard, soft, squishy? Is it rocky? Is it going to support me? Am I going to fall into it? Whatever, right? So good area for robotics. Musical robots. Scott Barton, we just hired him. All right, that's enough of that. That one I can't take for very long. All right, so all work and no play makes for a dull robot. What else? Brain interfaces. Wow, people who have suffered accidents and have trouble controlling their movements, if you can have them. Actually, this is now starting to work. There are cases of people who have prosthetics that they can control from thinking. Amazing. That's all robotics. We've seen the sample returns. We already saw that robot. We have support from AF Research Lab for a little surveillance robot. Got a couple of propellers on it. And we have walking robots. Okay. And let's see if this works. Poke your robot. So one thing that you're seeing here, I hope, is that people and robots do interact. Now, in the past, a manufacturing robot had to be blocked off from human contact with a fence or a screen, because if it hit you, it would knock your head off, right? And did not know anything about contact. It would just go where it had to go. But now you're seeing that robots and people are in the same space. So they're with us. modular robots that can configure themselves. Let's see. So here's one unit, but you could, in principle, stick many of these things together to make a larger, more capable robot. We built that on a 3D printer. Nice toy to have. There are the parts, okay. This robot looks like a big yo-yo, but it opens up to, to drive around. All right, so almost done here. When we started the program in 2006, before that we had one course, right? That was a course on industrial robots, and we had one lab, we had one faculty member, Kevin Wrong, we had no students, and we had basically no funding. Now here we are, we have 17 courses in robotics. When I was at MIT, I took the only course in robotics. They had one course then. Now they have more, so do we. We have 13 labs for robotics. 16 core faculty, about 34 people total involved in the program in some way or other. About 275 students, mostly undergrads, but also graduate students now, and 100 alumni, all those degrees, and we're accredited. So, what seemed to be science fiction 55 years ago, right? Robots in the home, ha ha, very funny. I'm here to tell you that that future is now here. Welcome to robotics. Thank you. Please, any questions? Yes? Right. Actually, grad classes run mostly on a 14-week semester basis. Undergrad classes, 7-week terms. So, but just take a semester and cut it in half, and that's the term. One thing it does is it lets students go off campus for 7 weeks. Call it 2 months, because they can go a little early and leave a little late. They can go off campus and do something at a project center and not miss a whole semester. They miss one term of classes. Works out pretty well. Yep, okay, another. Yes. You want to see that slide? Woo, okay. Right. Per term, yep. Oh, oh, credit hours, yeah. So it turns out Well, so for our accrediting body, we say one course is one course. We actually now count it a little differently, so think of those courses being maybe 2 credit hours, or maybe 2.5, right? Because you can get about 85% of a traditional course in 7 weeks. But you know what? 14-week semesters were not handed down on high on tablets of stone, right? There's other ways you can teach. You just have to change what you do a little bit. So it works. Right. Mm-hmm. Oh. Okay, I think I get your question. No, the whole school is on the 7-week basis. Okay, so every course is taught in 7 weeks. Diffie-Qs, calculus, right? So it's a matter of making sure that the courses can be taken at the right point in time for the students. So you asked about differential equations. Let's see, where is it? Diffie-Q is up, there it is, right? It's sophomore year B term, it's shown. So they take the Diffie-Qs, and they can then use that for taking controls the very next term, if they plan that out, all right? And they'll have it in time for taking Unified Robotics 3 and 4 the next year. So everything fits together pretty nicely. And there are many ways you could sequence this. And we have a lot of double majors, in fact. People who double majored in robotics and computer science, for example, or double E, because they've got a lot of overlap. So kids like it. And it's worked out. And of course, you can do this in a semester basis, too. So Lawrence Tech took our basic framework, and they're teaching their robotics major in 14-week semesters. That works, just a little different. No reason why not. Okay. Other questions? Yes?
So as part of the accreditation, you have this feedback loop of refining the curriculum and continuously improving.
Yes.
This curriculum, has it evolved?
Has the curriculum evolved? It has. Yeah. So I'll tell you, here's one way it evolved. We knew we wanted our students to take software engineering in computer science, okay? Because we figured, you know, if you can't write good software, you would have a hard time getting hired by a robotics company. And in fact, we didn't require artificial intelligence, because you can learn that and still get, you know, and if you knew AI but not software engineering, you wouldn't get hired. But if you knew software engineering and not AI, you could get hired. All right, so anyway. So we required software engineering, and our first pass we required algorithms, because of course you need algorithms for programming, right? Well, it turns out our students were failing to pass software engineering, despite having algorithms, because they didn't have the introduction to object-oriented programming, which you really need for software engineering. So we dropped algorithms as a requirement. This is a zero-sum game. We dropped algorithms and required instead object-oriented programming, okay? So now the kids can go and pass software engineering. So that's one thing we changed, as an example. We've added a freshman or sophomore level course in entrepreneurship. Before it was a junior, senior course, and our kids weren't quite ready for it, all right? So that's been a change. And another important change is we renamed the courses. So Unified Robotics 1 has been renamed to Unified Robotics 1, actuation. So when you see a kid's transcript, you know what he or she has done in that course. Right? So we've changed little things. We've changed our labs around. We have new lab kits and so on. So we've iterated and modified things. And we're happy with it. Yes? Yeah.
They made the wrong decision. Was that the bioinformatics and bioengineering? Was that the wrong decision?
Well, that was the right one. They picked that one correctly. But some of the other majors never really panned out, right? There wasn't enthusiasm in the faculty to make, let's say, system dynamics into an undergraduate major. Just no one really, I mean, someone was tasked with it and it just didn't happen. Right? And you know what? Probably not a good business choice of major. How are you going to get 18-year-old kids to come to your school for system dynamics? What does that mean? We tell a kid, we've got robotics. They go, yeah, all right, cool, you know, I'm going to come here. One of the other schools, they call their major mechatronics and robotics automation systems. Like, oh my God. Call it robotics, because your kids are going to anyway. What does mechatronics mean? I mean, who knows? In fact, our major is really a kind of shouldn't say baby. Our major is an undergraduate version of systems engineering. And we could have called it that, it would have been accurate, right? But what 18-year-old knows about systems engineering? You know, they wouldn't have come for that. Like, who wants to study that, right? Robotics, oh yeah, cool, I'll build these cool robots, and we'll have fun, we'll compete, and we'll stay up all night building robots. Okay, so that's important to get that, you know, into kids' heads and to market it really well. And we've got a really good Marcom operation now that can do marketing and communications. So those, they get it. Okay, yes?
Did you hire any new faculty members?
Oh, God, yes, yeah. So we've hired most of the faculty who teach the courses. So let's see. Torres Jara was at MIT and a Harvard postdoc. We hired him. Berenson was the one, the Berkeley postdoc and CMU undergrad. Chernova, Carnegie Mellon undergrad, grad, MIT postdoc. Fisher, RPI undergrad, double majored, Johns Hopkins PhD. Josh Onal, Carnegie Mellon PhD, MIT postdoc. Tashkent Padir, Purdue PhD, Steph Nessinger, UC Davis PhD. Who am I leaving out here? I think that's most of our hires. Right. Pretty good stuff. And if you had robotics here, you could. All right. So we're not going to hire all the Carnegie Mellon and MIT people either, right? So you could hire folks from the nearby universities like RPI, which has a really good but small robotics group. Cornell does some really cool robotics, right? I don't know if Binghamton does, but maybe. Carnegie Mellon isn't that far away. Right. Those folks won't be too scared of snow. They might enjoy living here and working. There's a guy at Vermont doing robotics. So those schools are turning up PhDs that you might have a good chance to bring here. Okay, so you can do that because they're not all going to go to MIT and Carnegie Mellon and Berkeley. Yeah. Okay. Yes. All right. Are they worried about the impact of automation? So, yeah, and that's a real good question. It's something that's on all of our minds. One of our students, for her junior project, organized a symposium on roboethics. What an awesome junior project. And she had speakers from Georgia Tech and the UK come and talk about ethics. So it is of concern. But I'd rather have someone who's thought about it. Because look, those changes are going to happen, right? Those robots will be deployed. I'd much rather have someone think about it, do the design, than someone who hadn't thought about it, all right? So will it displace workers? Yeah, they'll find other things to do, right? They'll have to. The economics means that it'll happen. But look, if you have robots in the factories here, you're displacing workers from Shanghai, not from Utica. Right? So if you made stuff here, you could ship it from here, design it here, have all the other ancillary operations here, the HR, the legal, the financial, right? All that, the marketing and sales. Engineering could all be done here, have robots build the stuff, happen anywhere. So, all right, so you could have manufacturing here, not necessarily a losing proposition, right? But it is of concern, to be sure. Do the courses cover that? I think they do. We offer them a range of choices, though. We don't have one course there. So some courses might have more of it than others. Right. But still, we do cover it to some extent. Thanks. Another question over this way? Yes?
Did your new hires grow your program, or did your program grow necessitating more?
Oh, yeah. That's did the faculty grow the program, or the program grow the faculty? It's a kind of chicken and egg problem. So you just have to do what you, yeah. So we proposed this curriculum. All right, so any students here? Good, no students. We had no clue. right? No one had done this before. So we just took our best guess as to how you might design a robotics curriculum. We just did it. And it made sense and it actually works. We've tweaked it a bit. For the most part, we've been able to hire faculty for the program, though. So we had a few key hires in the first couple of years, and that's made just a huge difference in getting some really sharp people on board for the program. And as we've grown, then you can say, oh, gee, we're teaching more courses, so we need more faculty. So those courses are taught typically twice a year. So there's enough need. And those faculty, you know what? We don't really recognize boundaries here. I mean, in fact, we actively disregard boundaries. I'm very proud of that. Who needs boundaries? Right? So when one of the faculty members says, I want to teach AI, my job is to make that happen. So even if they're robotics, by the way, it's not a department, it's just a program. So their tenure will be in computer science, EE, mechanical. So that's pretty clear, right? If they want to teach in their own home department, that's okay. We'll figure out how to move things around and accommodate them. But you have to keep those faculty happy and have them do what they want to do. And also teach the courses you need to teach as well. But it's manageable. Okay, thanks. One more question?
So on behalf of the lecture series, I want to present you, Mike, with the President's Lecture Series Medal. So this is just one of those tchotchkes that you can put, you can have the robot,
Thank you so much.
Have him you can put it on your, on the navigating robot.
Okay.
To all of you, I know this is Friday before our spring break, so this is an extraordinary effort to come out before everybody kind of breaks for spring break. So thanks for joining us at this lecture series. Our next lecture will be on the convergence of cybersecurity and psychological operations, PsyOps. And it will be Selmer Brinkshort from RPI who will be coming to do the lecture here for the President's Lecture Series next month. And I think we might have one more after that and then call it the year and then we'll pick it up again in the fall. So again, to all of you, thank you. And this was a great lecture, Mike. Thank you.
Thank you very much. It's a pleasure. Thank you.